Well, our second video is going to deal with 8 of the standard transformations. So you're going to have a basic building block function, and then it's going to be changed in some way. It's going to be transformed. And there are 8 major and 2 uncommon, but do happen occasionally, transformations that we need to be aware of. So let me start with x squared. I like x squared, it's a good function. And I'll call it f of x equals x squared, right? Call it that guy. It looks like that. Now, there are a number of different movements, changes to this function you could do. For instance, if you did y equals x squared plus 1, suppose you did that, and you graphed it, you might think, well, what does it look like? Well, if you use the same graph as you've got here, x squared plus 1 would look just like the original. All that would have happened to it is that with all its points would be moved vertically up by 1. So we would call this transformation, if I want to do it very cryptically, we would describe this as being move f of x equals x squared up 1 unit. Now, how they might describe this process is, they might say something like this. Y equals f of x, and then the transformation might be f of x add 1. So what you're really saying here is whatever the function is, in this case it was x squared, but maybe next time it's x cubed or absolute value of x, whatever it might be. And this new function, this transformed function, has the same formula as f of x, but then you add 1 to it. And that moves things up 1. So if I chose a different function, but kept the transformation, suppose I did, for instance, x cubed, which looks like that. And we did this thing. We did x cubed up 2. So what you'd imagine is take that point, which is on the origin, and move it up 2 places. And then, the best you can at least, and I'll do this as dotted only for emphasis, you move it up 2, and this is what x cubed up 2 would look like. Now, you could do it, one more version of this, move vertically upwards by 1. Suppose we took our function, in this case hopefully recognize it as the square root of x, and I did this to it. So we have y equals f of x, and then I said y equals f of x plus 4. And what would happen? Well, that guy would 1, 2, 3, 4 would now cross the y-axis at 4, and every single point, if I could plot them all, would all be equally moved up 4. So you'd basically get this guy. So one of the 8 standard transformations is move the graph up 1, 2, 4, whatever it might be. Well, if you can take a graph and you move it up, what would you think might be our second transformation? Well, let's do x squared again, which is this guy. Instead of moving it up 2 or 5 or 4, what I'll do instead is I'll move it down 3. Now, what would the function look like? What would the formula for this new curve, this guy here? Well, it would be that guy down 3. Or you could say f of x take away 3, where f of x, in this case, means x squared. So there is a very simple connection between vertically moving up in the graph and the formula for the graph. So for instance, square of x, if you move it up 4, you get the square of x add 4. X cubed, if you move it up 2, the new guy would be, actually, I probably shouldn't call that f, let's call it gx, would be called x squared plus 2. And in this case here, you've got that guy, and if you move it up 1, you have that. And in the same way that you can take a function, and if you move it downwards, as I have here, you can describe its formula, right? Its equation, whatever you want to call it, I would call it expression, as just the original take away 3. So suppose I have the absolute value as my building block. So there's my original function, absolute value of x. And let's suppose I have a new function, and it's going to be the absolute value of x take away 2. Could also have written this as f of x take away 2. Well, take that corner, that's an easy identified point on the graph, and then move it down 2 places to here. And if you imagine all the points moving down to this here, you should get absolute value of x take away 2. If we try one last one. Hopefully you recognize this one as the cube root of x. Suppose I wanted to draw the transformation of the cube root of x, and I told you that it was the cube root of x take away, say 1. And what would that look like? Well, take that point, because it's easy to identify where it is, move it down to here, and then basically imagine every point I try my best. Sometimes I'm not as good an artist as I should be. So if you want to move a graph up, the change is the original function plus how much you move it up. So this would move it up 1, this would move it up 2, this would move it up 4. This would take the original graph, the red guy, the original, move it down 3, move it down 2, move it down 1. Let's continue with this concept of up down, with 2 of our transformations. If I gave you this question, I want you to sketch x cubed take away 2. And you weren't going to use Desmos and do a really accurate picture. You're basically just going to take this guy, and you should be able to recognize 2 things. First is that the building block, the original function, would be x cubed. We know what x cubed looks like. Roughly looks like that. And then the same thing you would identify is, well, what does this do? Does it move it up 2, down 2, and various other combinations are possible? That means take this guy, and move it down 2 units. So take the one that you recognize, the easy identified one at the origin, move it down to its new location, and then basically try and draw the same curve again. And it might not be perfect because you're doing it kind of eyeballing it, but that would be it. Now, you can also use this property to identify what the equation of a particular curve was. So, for instance, suppose I gave you a sketch of this guy here, and I told you that that point there was 2. And the question was, what would be the equation of this function? Well, do you recognize its shape? Isn't it an x squared? But wouldn't x squared start life off here? Now what happened to it? It moved up to 2. And that would be your answer. So if you can identify what the basic building block shape looks like and its transformation, at least if it's a single transformation like this, you can actually write down what the equation of this curve is by using those properties. It's kind of useful. Moving on. Now, we've done move up, move down. This one is a little bit trickier. I'm going to do quadratic, kind of like this, and I'm going to have another function, a transformation of this guy, and it's going to be x take away 3 squared. So the original function, your building block function, nothing remarkable. That guy. Now you can certainly put that into Desmos and graph it, and you'll see what it looks like. And that's kind of helpful. And so I'm going to try and do that just to show you what it looks like. If you bear with me, here we go. Now, there is pretty normal quadratic x squared. Let me put in the new function. I'm going to call it g of x. And it's going to be equal to brackets x take away 3, close the brackets, square. And there's something that is interesting. The new curve, the x minus 3 in brackets squared, is a transformation of the original red one, x squared. But look what happened to it. It didn't move up 3 or down 3. In fact, it moved to the right 3. You see the original is here. And the transformed blue one is basically from here to here is 3 units. It moved it to the right 3. So it was here. So if you put x take away 3 squared, so it's basically x squared being transformed, you see the x is now being replaced by x minus 3. This transformation moves the graph to the right 3. In fact, if that was x minus 1, it would move it to the right 1. If it was x minus 1,000,000, it would move it to the right 1,000,000. So let's try another function. Suppose I have the square root of x. And the transformation function is the square root of x take away 2. So we start with the square root function, which is this guy. This transformation, right, this guy is now being turned into that one. That tells me it's a move, yep, to the right 2. So that guy at the origin is now going to be here. And then every point on that curve would get moved to the right 3. So it looks something like this. That I know is counterintuitive. It looks like if you were taking 2 away, if it was any kind of movement, you would think it would move everything to the left 2, but it doesn't. X minus 2 actually moves the shape to the right 2. And that is our third transformation. So we've done up, down, to the right. Of course, we're now going to do it to the left. So let's do absolute value of X. And this time, the transformation is going to be absolute value of X plus 3. Here's X and Y-axis. The absolute value function just looks like a big V. Now, based on what happened in the previous questions, when there's an X take away 3, it moves it to the right 3. It's now an X add 3, right? So the X is being replaced by an X add 3, the formulas, as you can see. That makes it left 3 units. So you're going to move it to the left 3 units. So you imagine that point. You go 1, 2, 3. That takes you to here. There's your guy. And that's what the absolute value of X add 3 looks like. It's a transformation of the absolute value of X, moving everybody 3 units that way. And just to convince you that that in fact is the case, bear with me. I will do it here. Here is the absolute value. I think it can take that notation. Yep. And then the absolute value of X add 3. If we move this a little bit, so it's a little bit more centered, can you clearly see that the red, the original absolute value of X function, has now been moved leftwards 3 units. So how about one more of these? Suppose I had a function, say X cubed, and the transformation function would be X plus 1 cubed. And without Desmos, if I wanted to just do a rough sketch of what that would look like, hopefully we recognize what the cube function, I should say, is. And this guy is moved to the left 1. It'll be here. And basically, you try your best. There you go, it's not too bad. That's what g of x would look like. Now, you can write this piece of information in a number of ways. For instance, you could just describe it like that. So here's your x cubed. This would represent x plus 1 cubed. See this guy up here? It could have been x add 3. these two guys that we've done here, this fella is basically f of x taken by 3. And this one is f of x minus 2. So if someone just gave me a kind of generic formula and went and said, look, I have a function y equals f of x, and these are the transformations. I'll call them 1, 2, 3, and 4. We'll call the function g of x each time. If this new transformed function g of x, it might be that one. It could be that one. We should be able to say, right, you take the original graph, whatever it looked like, right? Maybe it's an x squared, but maybe it's some W shape or whatever the graph might be. We can still use this representation because we don't have, for instance, maybe a formula. This would be move the graph up 3, move it down 2, yes, move it to the right 4, and finally move it to the left 1. And so we can represent transformations in this very nice functional way as well. Well, we're halfway through. There are 4 more to go. So the guy I'm going to use this time is going to be the square root of x. And the transformation that we're going to do is to add a negative to the formula, and I'm putting it there. I call this a negative on the outside. That's just my name for it. So if the negative is on the outside, what would the transformation look like? Well, here is the original, right? If you graphed this guy and you did it in Desmos, you'd be able to see what it's like. I want you to think for a moment before we actually even go there, and maybe you could come up with what you believe you would get. So obviously the y coordinate is now the negative of the square root of x. And what you get is this guy. So if you graph y equals negative the square root of x, you get this curve. And if you try to describe what this transformation is, it's a reflection. Can you imagine the x-axis as a mirror? The original y equals root x is being reflected in the x-axis, and it's now here. We call that, its correct description is a reflection in the x-axis. Don't call it flipping it upside down. I know what you mean when you say that, but that's not really a mathematical term. Just call it a reflection in the x-axis. And that's a good thing to call it. That's the proper thing to call it. Now, let's try another one. Suppose it was x cubed and you wanted to sketch that guy. Well, we know what x cubed looks like. It's that guy. And we know this is a reflection in the x-axis. So what would essentially happen is that this guy would come down like that, and this guy would go up like that, and you would now have your transformation. And we call that reflection in the x-axis. I don't know if you've noticed as we've gone through these, but these transformations tend to go together in pairs, up and down, left and right, reflecting the x-axis. Well, what does a reflection in the y-axis look like? What does that transformation do? Well, let's pick the square root of x, which looks like it's like that. And now reflect it in the y-axis, it would look like that guy. And what is that fella? This guy here has that formula. And I call this, just my made up name, the negative on the inside, right? Negative on the outside, negative on the inside. This gives you a reflection in the y-axis. Yeah, let's try another one. Suppose I do this one, which is a little bit weird. So there's the original. This is going to be a reflection in the y-axis. So why is this going to be weird? Well, just watch what happens. If you take y equals x squared and you reflect it right in the vertical axis, oh, you see that they're actually, one is just superimposed on top of the other. So you can't really tell that it's being reflected, but basically all these guys are over here and all those guys are over there. But when you join them all together, they just superimpose on top of each other. You end up with the same curve. It's kind of interesting in itself. And that is us done with reflection in the x and reflection in the y-axis. So put those aside. Let's do a quick recap. So that's the 6 transformations that we have covered. Up 3, down 2. Yep, it's to the right. Right 4, left 1. Reflect. In the x-axis. reflect in the y-axis. So who are the last two major transformations? Well, here they are together. So if you take the original function f of x, but you double for every x, you double what the y value is. That's essentially what this is doing, doubling the value of the function. That would be a transformation. And if you take this and you took the corresponding points on the curve, but you took their y coordinates and you essentially made them a quarter of the height, you'd get that one. We call these two, the first one, it's called a vertical stretch by a factor of 2, and this is called a vertical shrink by a factor of 1. Okay, so let's see what that might look like. Who shall I pick? Oh, let's pick x squared. So here is x squared. Now we would like to do that guy. Well, that point there has a y value of 0, and if you double it, you still get 0. But that guy there might be like 1, 1. He gets doubled to 2, and that guy gets doubled to 2. So what the thing looks like is that guy there. It's basically, imagine the red, the original x squared was made out of plastic or something, a rubber band, and you grabbed it and you pulled it up, you gave it a wedgie. It would be a vertical stretch of 2 in this case. It would look like that blue curve. And suppose you wanted to do 1/4 x squared. Right? So here's your original. If they look different, it's just a scale issue. If you take every point on the curve, and in particular you focus on their y values because the x values stay the same, this height becomes a quarter. This height becomes a quarter. This height becomes a quarter. So do these heights. So what you end up with is a guy that looks like that. And that's very, very roughly what those would look like. So we have 8 major transformations. And the two that I've not spent any other time on are horizontal stretch by a factor of 2 and horizontal shrink by a factor of 2. So one of them you stretch it this way and then you push it in that way. But you can look those up when you like. Okay, so that is the end of this lesson.